Share screen. All right, can people online see my screen now?
Yeah, we can see it.
Perfect.
Thank you.
All right. So, thank you, everyone. My talk is about the old and the new, as you can judge from the title, geometry and foundation models. I'll show you how they can come together to build a general pre-trained model for 3D vision. That's really important for driving and including some of the, automated driving, not completely autonomous, also autonomous, but also robotics at large. And indeed, geometry is at the heart of autonomous driving. For all of you that have worked on this, you know this, but more broadly, also robotics. And whether it is on the road, in the factory, or in the home. And so these are all topics we care about at Toyota. And there's actually a lot of them, a lot of commonality between those topics, including geometry. The same can be said about machine learning, which is of increasing importance in case you have been living under a rock, not just in perception, but actually everywhere across all parts of the driving stack and the robotic stack in general. And as also you've probably seen, if you're on Twitter, I'm sorry, I know it's difficult times, but also exciting times because the growth is rapidly accelerating. It's everybody is kind of a mixture of excitement and exhaustion because of the second part of my title, foundation models, which are now very rapidly democratizing machine learning. But first, because we're a scientific conference and we're not on Twitter, what is a foundation model? So I think we're too many to just ask for shouting definitions, but just raise a hand if you think you have a pretty good idea of a definition of what a foundation model is. Yeah, not surprised. Nobody raised a hand. Okay, so my definition, the one that I like, is the one that was proposed in the actual foundation model paper by Stanford, the Center for Research on Foundation Models, that coined the term. So I think it's fair to ask them what is their definition. And I like their definition, which is simply train once and then use for many tasks, right? And that's a bit different than the standard machine learning, which is you train a model for every specific task, you collect a data set for every specific task, right? And the main reason for the excitement there is that it can amortize the cost of learning and enable very rapid developments. I mean, ChatGPT, there's a reason why it got to 100 million users in 2 months, right? It's because of this, because it's trained once and it's been used many times. So current foundation models, of course, first talk in the morning, your first mention of ChatGPT of the day, you're going to hear much more about it for sure throughout the conference. You've seen it, right? And the thing that you might not have seen, and especially 2 weeks ago, I was giving this talk actually at ICRA, conference in robotics, is that there was the same thing, ChatGPT everywhere, and not just because of the hype, but because there are plenty of uses already in robotics. For instance, for user interfacing with your voice or with text. Also, a very popular task in robotics is for task specification, how you say a high-level task, and it decomposes into subtasks and behaviors the robot can do. Also, one thing you'll probably see a lot of this week at CPR is open world recognition, right? But it's mostly limited to language right now. I know we're going to see a lot of things this week, and there's more and more multimodal language models or vision language models, VLMs. We'll add an acronym to your long list of acronyms to remember, but still the main success story is in language. And so now, I think that's also a pretty non-controversial statement, but and the more interesting scientific question would be why? Do people have an idea? Again, same thing, just going to ask you very high-level questions, you can show a raise of hands. Do you have an idea for why? Is it mostly just language that's where you have a foundation model? Okay, cool. Now we get interesting. People don't have a clear definition of foundation model, but they kind of know why it's happening because you're all experts in the field. And so you realize that it's the data. So I think the people that raise your hands probably because of the data, right? And there's, trained on the web, et cetera, et cetera. So using internet, and actually for the VLMs, and we have a long history of that in computer vision, like big data sets like ImageNet have been around. They've been the engine of progress for the past decade. Before foundation models, right, to deep learning, but now the data sizes have increased by, I think, roughly 2 or 3 orders of magnitude. to get to the current foundation models. But going towards embodied intelligence for cars, robots, etc. So like, right, embodied intelligence is intelligence for physical machines that interact physically with people and things and the environment. That's going to require, at the very least, 2 or 3 or 4 order of magnitudes more. And honestly, I don't think anybody can do that because you have to construct millions of, hundreds of millions, a lot of robots, and then have them collect data all the time, etc. So I think just the cost of that is a little bit insane if you actually do the math. And so you'll realize very quickly that we can't just rely on data alone if we care about cars and robots and physical machines. And so we need to fill the gaps in our data sets. There's always going to be gaps, whether things that keep happening and the world keeps changing, or safety critical stuff, happens at some statistics, but you don't have in your data. And so we need to complement these gaps in the data with what we already know. And this is an approach we've been pushing in the team, and that I'm going to talk to you a little bit about today, that we call principle-centric ML. And here, the idea is we combine data, machines learn from data, but we have something to teach them, like safety, etc. Or physics. We know about physics. Newton existed, physics of light. There are some things we do understand, and they're not just constrained on the learning system that needs to be completely free. No, their constraints are good sometimes. But luckily, for physical machines, like cars, robots, etc., there's a lot we know about the world. There's a lot we have discovered. Again, F equals ma. We know there's certain things we know, and we have these principles. And the question is, how do we use them together with machine learning? Right? Principles, what we know sometimes in equations, and then machine learning from data and mostly weights. So the difficulty is really the combination of these two ideas. And this is what principle-centric ML is about, finding ways to combine those. So in this talk, I'll focus around one particular area of principles that we've been working a lot in the team on, which is relevant for both, as I said, the road, factory, the home, you name it, any kind of robot, and that's geometry. So again, just to wake you up, get the coffee kicking in. Who knows what this model is? Oh, come on, you're at a division conference. Don't be shy. Who knows what this is? You're using it all the time. Okay. Can someone shout what the name is? This one I'm going to challenge someone at least. Come on. Yes, pinhole camera model. Thank you, sir. You win cookie points. So, do you know now? Second question. How old is that model? 40? 40 years old. Okay. Someone says more. Someone says less. Who says 150? 150? I feel like an auction. 150, 150. Who says better? 400, 400. Who says better? We keep going back in time. Come on. You're far. You're far. Don't be shy. All right. It's like thousands of years old. It's like Mudzi, Chinese philosopher. There's like writings that he has figured it out. Aristotle had figured it out. He has actually drawings. So it's really old. It's really, really old. So yes, humanity has been around for a while. We're not the first people to use what's between our ears. There's a lot of stuff we know about the world, and we have known this for a very long time. It's a very powerful model for understanding geometry. But I say model, and some of you might wince because it's not really a machine learning model, or the main use of the word model that we see today. And why is that? Because we cannot train this model, right, on data to make predictions for us, say about how far objects are in the scene. I mean, it's a 2D to 3D, 3D to 2D kind of model, but it doesn't make predictions. So again, so just to illustrate that, we have machine learning models and geometric models are very different in nature. How do we combine them? And this is really what our methods are about, how we can merge these two types of foundations, data-driven transformers in particular, right? So the main models, the main workhorses we found to work well now, and human-derived principles to learn a geometric foundation model that, again, according to the definition, is trained once and useful for many, many tasks. So I'll drive you through the main way the community has found, ourselves, others included, on how to inject some of these fundamental geometric principles into learning by using self-supervision. And actually, it's a very general way, just like in NLP, but this time we're using geometry for 3D vision models instead of autoregressive language models. So we start with two frames, the current frame and an adjacent frame, so T-1 or T+1, depending on what you want to do. And what we want to do is we want to take a depth network, right? So again, ConvNet, you name it, or transformers nowadays, and you feed the current frame. And what you get is you get this little range image that you see here. You might have seen a lot of visualizations like this. For those that haven't, it's basically just showing you for every pixel how far a ray would intersect with the real world that's bounced from that pixel. And yellow is closer to you, darker is further away. You also take two frames and you feed it through another network, which is called the pose network, which predicts you the ego motion, how much the camera has translated and rotated from one frame to the other. And you get a predicted pose rotation translation. Now, with these two predictions, you move on from machine learning land and into geometry land, because now you have something that you can do geometry on. You have RT, you have depth. So what you can do is you can do view synthesis, which means you can project information from the current frame onto the adjacent frame by projecting from 2D to 3D and back, right? So this is what you see the predicted point cloud, and then we can just synthesize the adjacent frame from the current frame. And this is all differentiable, so this view synthesis operation. And so the nice thing is that this will be accurate. So the reconstruction of the adjacent frame will be accurate if and only if two things are accurate. Number one, geometry, but that we know, we have proofs, right? Number two, it's the models, and that we don't know, we're trying to learn them, right? So if you're making a mistake in your view synthesis, meaning that your synthesized image, the pixels don't line up with your target image, your adjacent image, then what happens is you're getting an error. That error gives you a gradient because every operation here is differentiable, and you can backpropagate to update the weights of the depth network and the pose network, right? So backpropagate through the geometric constraints. And so by minimizing the photometric difference, which you see here, which is called the photometric loss, right? Which is the objective we use in self-supervised view synthesis. In this case, you have, if you're using NERF, you have different types of objectives, volumetric objectives. These are all, objectives that you can combine, but this one is the main workhorse for us. Then, you can basically just, again, backpropagate through that loss, which you see here is the per pixel loss. Brighter means higher loss. And you can optimize for the parameters of the model. So that's a very general description of the framework. Why is it very general? A lot of people, including us, have made a lot of papers on this and found that it works really well across a variety of architectures, data sets, and even tasks. And so I would encourage you to check out, all our code is open source, and you can check it out. And it's been very successful for us, both again scientifically and practically. So this is like images taken from a fleet of cars, our fleet of cars in Tokyo, actually the Odaiba region in Tokyo, and it works to see the rain with like pedestrians crossing, trucks, all you want. It's fully self-supervised, running from a single camera. Now, it wouldn't be a foundation model if it was just working for one thing. Again, train once, used for many tasks. And so what actually we found, and that's the power of open sourcing your ideas, both publishing papers and the code and the models, is that you get to see people do crazy things, sometimes at your own company, but sometimes outside. So it works in the snow. I think some Reddit user use it for their, extreme biking videos. We have actually shown we're pushing the limits of where this thing can go. We've shown this can work underwater, which if you think about it geometrically, it's a bit insane because you have the water acts as a kind of changing lens. So here you have to use a little bit more complicated geometry than the pinhole camera model. But we show we can go from driving to diving. So that's a nice multiple use cases that you see. Crazier, driving and robotics are actually fairly different in terms of one fundamental geometric aspect, which is scale. You care about things that are far away in driving typically, and you care about things that are really close in robotics. And so actually so close that it's inside the sensor. So this is actually one of the sensors that we invented at TRI, the robotics team, led by Alex Alfred, which is about like an inflated latex bubble that acts as a tactile sensor. And it's actually a visual tactile sensor. It has a camera inside the bubble, inside the end effector. And then the deformations, the shear on the bubble as it touches objects you can get depth image from inside using the similar ideas. And actually, we look at more than just cars at TRI, as I mentioned, because we look at robotics as a research challenge for a lot of broad applications at Toyota, the road being one, but again, the factory and the home. And so one of the challenge tasks we have, the robotics team has, led by Max Bajashaya at TRI, is have a grocery shopping robot. Not that you will be able to buy a Toyota grocery shopping robot. I want one, but we won't build one. We're building research prototypes that enable us to push the limits of where we can go with this technology. And so here, same ideas apply indoors, outdoors, yeah, you can see supermarket reconstruction here. So, as I mentioned, this is important work across many diverse domains and tasks. We're not just the largest car maker in the world, we want to become the largest robotics maker in the world. And so, as I mentioned, we have this challenge task for robotics. We actually have completely in-house built robots. They take a list of 10 shopping items and then they try to go shopping with a fake supermarket in the office, which is what you're seeing here. And again, the reason is not really making supermarket robots, it's a research challenge. And then the ideas they pan out transfer to this robot, which you would see in Toyota factories, which is actually industrial robots that will not just be helped to make cars. Actually, the robots that make cars are very constrained in their programmation. They're doing very repetitive tasks, but there's a lot of tasks that involve a bit more complicated, like here, the tasks you've seen. So how do we go from supermarket to factory to the road to the home? This is why we need foundation models, because it's a very big company with a lot of applications. And so the reason, again, why foundation models work so well there and why there's such excitement of the promise is train once, use many times, is really rooted in zero-shot generalization, right? I think the biggest lesson the community has learned now is that if you need too many samples to fine-tune, you're not fine-tuning anymore, you're overfitting. And really good performance in terms of fast adaptation to a domain, to a task, actually is rooted in strong zero-shot performance, which is why you need models that can do the task zero-shot, not perfectly, but decently enough to get started. And so besides data, obviously there's an important idea to get a good zero-shot performance. So obviously data is needed, because if you're completely out of domain, you know, it's still your good old machine learning, it's still statistical pattern recognition, it doesn't extrapolate. But you might have to interpolate between fairly distant data points. And so you need, again, to fill in the gaps with these data points with more geometry. So again, waking you up a little bit. Who knows what this is? All right, okay. So someone make Andrew Zisserman happy and tell me what this is. This F. There you go. Cool. Good. Excellent. I'm at a vision conference. Nice. Robotics conference? Sometimes. No, people know this actually. Okay. So this is the fundamental matrix. It's a 3x3 matrix that encodes uncalibrated epipolar geometry. How to go from one point in an image to the epipolar line in the second image. And this is how generalized stereo is solved. And again, geometric principles are actually a superpower. They're, like, if you think about it, it's the condensation of millennia of human intelligence in beautiful mathematical form. So this is the ultimate form of pre-training. This is the ultimate foundation model, right? So how do we use it in today's foundation models? So we've looked at the pinhole camera model, which was used to underline the view synthesis objective. But now we can use actually the fundamental matrix and the epipolar geometry. And this is what we did in our recent paper called the depth former. Whereas in the previous works, we leveraged just camera motion during training for self-supervision. We can now, actually leverage it at test time as well to do multi-frame inference, because vision-centric very often in this community means image-centric. And everybody's like, yeah, and later I will do video, and then they move on, and then we're stuck with images. So one thing that I would encourage you is to actually just go for video. I know it's harder, and then it might be risky, but actually if you do, everything is video. Honestly, like in our field, it's images are sure Instagram, etc. But if you care about robotics and whatever, it's like every image is a frame that comes from a video. Embracing that fact gives you an edge. if you're brave enough to go after it. So there are a few challenges with that, right? So there's a reason why people stick with images, it's easier. But the main idea here is to use the epipolar constraint that I just mentioned and transformers to predict depth by learning self and cross attention layers, which you see in the middle here, for matching along epipolar lines, along multiple frames, right? So you can imagine you're searching along an epipolar, say that pixel matches to another pixel along that epipolar line, which pixel? And you can imagine that attention along that epipolar line provides actually a very nice principle solution to solve the matching problem. You can also use geometry implicitly. So that's also a new thing, actually from the same discipline that wrote the book on these equations, etc. Done some really exciting work that opened up the community to this idea of implicitly conditioning on geometric information versus making hard constraints on the geometry, right? Which is a bit sensitive to, let's say, calibration and stuff like this. So this approach, which we built upon in our paper called Define Depth Field Networks, using geometry implicitly to gain a little bit more robustness is actually a general idea. And it works very well with transformers because we found ways to condition on position encoding, etc. But now we can condition on geometric information. So again, instead of restricting the search along epipolar lines, we use our geometric knowledge as input level conditioning. We feed it as input instead of constraining the search, right? And the cool thing with that too is we can do all other kinds of bag of tricks that we found to work for these models, like data augmentations, but we can then do now in a more 3D aware or 3D principles, and still solve the same task as I showed you earlier in terms of view synthesis. There's actually recent work now where we're mixing more ideas, I think the Delira paper, where we're also combining with other types of losses, looking at light fields, looking at volumetric rendering, etc. So all these transformers, all the stuff that I've shown you so far, can use geometry because we have an explicit model of it, right? So this is why we have what we know. What we know is in the form of these equations, etc. that I've shown you, the null camera model, epipolar geometry, and we can leverage them inside the learning framework, if not directly inject them into weights, because we have an explicit model for that geometry. But often we don't know it perfectly. So the reality of it is I kind of like bamboozled you a little bit because the pinhole camera model is not really that useful of a camera model in practice, but small deviations from it are. And so you can marry the old and the new still again, which is kind of the topic of my talk, to learn more principled camera models, more general camera models. For instance, extensions of the pinhole camera model, the one I'm showing you here, which I think is kind of used almost everywhere in all the robotic cars, at least that I'm familiar with, which is the double sphere camera model, which is from the family of unified camera model. This one is very neat because it just adds one parameter to the camera intrinsics. But you can even go crazier if you have some compute budget, I would say, at inference time in particular, and you can learn projection and unprojection functions per pixel, because that's essentially what the camera model does for you. It tells you how 2D and 3D relate to each other, both back projecting and projecting. And so you can say, well, okay, the mechanics of geometry is projection and projection, but the actual functions for projection and projection, I can learn them per pixel. And this is our neural racer for this paper. And what we further shown is that these type of camera models, actually, this is where the old and the new come together. We can learn them from data end to end with the view synthesis objective. So you can do the self-supervised self-calibration as you're learning the depth and pose networks, right? Basically, you're just you're unfreezing the parameters of the camera model and you're back propagating all through to them to update them. Again, little dark knowledge is you do need some good initializations for them, but honestly, pinhole intrinsics, even the default ones with alpha resolution and center optical center, that works pretty well. Beyond video-based 3D vision, I know it's vision-centric, and vision-centric typically means pixel-centric, which is a lot of what I've shown so far. But as you know, in robotics and driving, depending on the platform, you might have access to some more powerful RGBD sensors or maybe some LiDAR sensors, maybe not great sensors, but you have sometimes some 3D information. And definitely at the training time, you do have that information, whether CAD models, simulation, etc. And I gave a talk yesterday at the synthetic data workshop, and so there's plenty of times where you have 3D vision, 3D information. And so we actually have been working also on building more pure 3D foundation models. For instance, for efficiently representing and generating many shapes from 3D point clouds or meshes or CAD models. This is the road model you're seeing on the left here, where road stands for recursive octree autodecoder. But it's basically a generative model of shapes that can include many shapes at many different levels of resolution. And we can work also with RGBD. I think almost all robotics applications have RGB cameras. And so this is the shuffle paper that we show on the right, which is not just about geometry, but it's also about texture shapes. So appearance and geometry together. We also present a paper at the CPR where we do things for articulated objects. So it's called CARTO, and also with multiple objects interacting with each other and predicting the dynamics. So there's a couple of things I'll mention at the end for this talk. Of course, I said foundation models, remember definition, train once, used for many tasks. So far, you could argue again that I'm playing a little bit with many tasks because I said many domains for depth and pose, which can be used for many tasks. And actually, this is what we've done too. So geometric foundation models are useful as is, but for things like object detection, for instance, we found them to be very important. And here, there's interestingly a commonality again with NLP, especially with the methods that show you can get good fine-tuning. So we've done DD3D, DD3D, D2, and VDES, which actually Dan is going to talk about today. It's presented at the MEN conference. One of the commonalities we found here is that pre-training using these geometric foundation models as the start of the backbone actually turned out to be really helpful for these papers. And again, we'll talk more about this and about specifically the viewpoint equivariance and data augmentation and stuff like this later. So in conclusion, I have shown you that there's a life beyond ChatGPT for foundation models. It doesn't have to be all language. Everybody doesn't have to become an LLM person, even though I think everybody's becoming a little bit LLM flavored, myself included. But a part of the recipe between the LLM world, the large language model world, and our world is that there's a part of the recipe that's in common. And that part of the recipe is what I talked about at first, which is self-supervised pre-training on a lot of data. But here we can go beyond data, what I've shown you, right? Because the language models, remember, it's just predicting the next word. What we're doing is we're predicting the next frame, but not just per pixel, but through geometry. And we're backpropagating through geometric principles that are used in our losses, in our network. So losses, the view synthesis loss, right? Using the warping dimensional camera model. Our architectures, talking about define, deformer, where inside the architecture, you either have search along the epipolar line, with self-attention and cross-attention along the epipolar line. That's the deformer. And on define, you condition on geometry and the inputs and using data augmentation, 3D data augmentation. And so there's ways you can use these geometric principles. You don't have to throw away what you know and just predict the next pixel. You can use these techniques. And I've given you some ways, and I'm sure you're going to discover many more ways being so influenced by this great talk, I'm sure. Please show me. But the question is, are geometric foundation models, because just geometric foundation models now, are they enough for autonomous and useful machines, like cars, robots, etc.? Like, clearly, we want more than just our models having an understanding of geometry. And so what we want is more general, and that's the thing that my team has been working on for the past 6 months, a year now, in terms of generalizing this approach to embodiment in general. Not just geometry. Geometry is just physics of light. We want much more than that. And I think here the recipe, the same recipe actually applies, and that's our main scientific hypothesis, is that we are working from the angle of getting as much data as we can, but it's not going to be enough. So complementing with other form of principles. And here there are 3 big areas we're working on. Obviously language, because we don't live under a rock. And we know that there's actually surprisingly, and especially the jump from GPT-3 to GPT-4, there's actually an increase in grounding in those models, which is kind of interesting. And a lot of the critique we had seen, and I myself had formulated in the earlier generations, seem to kind of wash away. So there's something here we don't completely understand, but there's some notions that are starting to emerge in these language models. And so I think it's very exciting as a scientist and as a practitioner to try to exploit that and see where it leads us. Now, as I mentioned, it's not just geometry, it's not just camera, it's actually embodiment. We don't want to perceive, we want to perceive and act. And actually, if you know a little bit about cognitive science, you know that these two are very intermingled. We're sensory motor machines. And so we're looking at more than just images, more than just language. We're looking also at like multimodal models, combining the two, but also combining it with action, right? So vision, language, action, those three need to come together. And so we've been working on that. And finally, as soon as you give action, physical action and interaction with people in the world, then you need to think about safety. And that's always been a big focus of area of work for us, especially within, the set of principles in control theory is actually really important to look at because control theorists have a lot of knowledge over decades and decades and decades. And so how do we combine that knowledge with learning? Actually, last week, there was the L4DC conference, the Learning for Dynamics and Control, where we actually won the Best Paper Award for a paper called In Distribution Barrier Function, which is the same idea as what I've shown you right now, which is we're combining a core principle of control theory, a tool actually for safety, which is called control barrier functions, and ported it into learned high-dimensional spaces where we can encourage robots, a visual motor policy, to stay in domain and go out of distribution states, but in very high dimensional spaces. So there's a lot more than I have the time to talk about now in terms of combining principles, not just geometry, but control, any type of principles, together with modern machine learning. And so in summary, my team at TRI is working on building an embodied foundation model, whatever that is. And I appreciate that you all were, humble and didn't say, obviously, I know what a foundation model is. Nobody really knows, but we know one when we see one. Again, the definition training once used many times is great. And we're going to know it when we see it, but we're actually working towards it. And what we know for sure, where the scientific approach is really well-grounded for us, is the principle-centric approach. We have two teams. We have a vision team, where the goal is to learn to see and understand the world. We have an interaction team, which is a fairly new team for us, looking at language, safety, and embodiment. And obviously, as I mentioned, the sensory motor loop that our robots are, whether in the car, on the road, in the factory, in the home. These two are very intermingled, and so actually people work very closely across the whole team. This is the people that actually do all the work here, and we have many amazing collaborators at many American universities, and all the code and data is available online. We have a variety of also like blog posts. If the papers are maybe too detailed or you don't know for sure if it's interesting or not, we have generally high-level blog posts for that. We also have one that describes all the papers we have at CEPR. If some of the pointers you've seen here didn't have time to catch it up, you can go there and you can see all the papers that we're presenting at this conference. And because there's still a lot of work to do. If you're interested in working with us, please let us know. Oh, and one more thing, because I know it's a driving workshop, so here's a cool driving video. If it plays, I don't think there's a sound, so maybe I'll have to do the sound effects. So even though I mentioned that my team in particular, our research is more general than just for cars, we do work on production cars and partner with people. Some people actually here at this conference, if you want to talk about what does it take to deploy things in 100 million car fleet, if you can talk to them, it's hard. But we still have some research also, of course, that's very focused on driving. In particular, Avinash Balakamban's team, TRI, is looking at driving and people working in tandem to do very hard things like drifting, because that's safety is, as I said, the goal again. And so looking at where is safety really hard, not when you're drunk, but not these kind of things, but when really we don't know how to solve that issue. And I think in terms of control, drifting is a really hard one. And they have an autonomously drifting car, which I just showed, which is pretty cool. Happy to take questions.
Thank you, Adrien. So now, so I have any questions. We can open
So to start with foundation models, I'll go back to the slide again. Maybe do a little pushback and maybe a little bit comments. Then I will also ask for a criticism of my comment. So one of the pragmatist properties of a foundation model is they give us the content or the corpus that we don't necessarily have access to, right? I mean, say for example, I don't know Arabic, but the ChatGPT foundation model is a lot of idea and understanding of aspects
Okay, yeah.
of that context. So what you're showing, and actually that's true for a lot of vision models, probably is falling behind in that sense. Like, right? I mean, you don't have in vision access to a lot of corpus that we lack, right? And you sort of hinted to that. Like, I mean, we need to deploy like Tesla. Maybe Tesla the only, I don't know, the real company, like one of them like that. And so, do you have principles? Do you have ideas? Do you have a direction, or do you have maybe I don't know, have you tried, or do you have a plan to tap into that input misalignment? I'm going to call it input misalignment, because we cannot really use the other visual sources that are out of our corpus for our own purposes.
So that's an interesting and deep question. So what I'll say is this: is that so we don't have. You're right that we don't have. I think nobody has found like an equivalent to ChatGPT, right, as a foundation model for even just vision, but more generally for robotics. That was the #1 thing people were talking about at VCAD in London a couple of weeks ago, right? Everybody's talking about it. And clearly language has a role, vision has a role, action has a role. We have the web for the data for language, so we figured that one out, I guess. But for the other ones, right, we don't know. So that's I think those are all fair statements. We do, what I propose in this talk is that we do potentially have a recipe, which is a self-supervised recipe using geometry as a source of self-supervision. You could apply this to all the videos on YouTube if you are ready to boil the ocean, for that. I think we don't need to, because there's a lot of crap on YouTube that we don't care about for robotics and driving, etc. So we found an approach that kind of worked on all the driving data we could get. My statement is, from a first principle standpoint, you will never see all the data you need, simply because at some point you have to ship and new things can happen, right? And so you have to, so that's why there's an interesting line of work, and there's some workshops here at TRI on continual learning and these kind of things. But they're like, I think scientifically very interesting, a little bit far for our applications, where you don't want a car that gets an update in real time and you don't know what's going to happen because safety, etc. So you do need to have some kind of form of like pre-training, a big pre-training once, and then some adaptation, right? And so I think that what is this big pre-training on what data? All the data you can get. Is it going to be enough? Never. We have 100 million cars on the road. They see new things every day that no other Toyota has ever seen. And that's the largest fleet of cars in the world. So robots, they're so far away from this, right? So a robot in every home that's going to be useless for decades before it has enough data? No. So I think there's going to be a lot of gaps in the data, and you can't always be in research mode. At some point you want to deliver on the promises and actually ship. And so to me, this is basically where you need to fill in the gaps that you have in your data, whether for practical reasons, because you have to deliver, or because it takes too much, or because new things keep happening. It's a very, let's say, rich and ever-changing environment. Like homes are changing a lot. There's a lot of new objects in your home now that they didn't have 10 years ago. And so I think that you have to look at what is shared. And that's why for us, actually, generalizing to beyond driving has been very exciting, because what's common between the road, factory, and the home? A lot of people say nothing, run away. But actually there is. Gravity is a constant. People is a constant. Nobody wants to be hit or hurt. But even more positive things, like people want helpful behaviors, they want to interact. So I think that if you look at the commonalities, yes, you're going to have something that is less useful, like the previous age of machine learning, which is if you build a data set specific for your task and it's big enough and you supervise it enough, it's going to be useful for that task. Now you have to let that go a little bit, the usefulness out of the box, end-to-end, one step. You go back to what is common, what is shared, and what do I want to not reinvent the wheel across robots. Safety is one, physics is one, human interaction is another one. How do we get there? By combining data across these very different fields, which is very exciting from a machine learning perspective because they don't overlap, right? It's not one big continuum, messy continuum like the web. And then the second is, what do we actually know and how do we inject it into this? So I stand by what I said. Essentially, you're never going to have enough data, but you don't need to. And also, if you don't need to, why boil the ocean with all of YouTube, right? I mean, if you want to do that, I'm sure Google is trying or has tried, or I don't know. But I think it's just, first, I don't know if that's responsible. Second, I don't know if that makes a lot of sense. You don't need to. At least that's the hypothesis we're pursuing.
Thank you for your talk. I think it's a great idea to use foundation model in the self-driving scenario. And in your talk, it seems like you use that for test estimation. So do you use that for other purpose, self-driving?
Yeah, so in robotics in particular, so I don't have new results to show you yet, or maybe offline if you want. But we've been working a lot on ideas in robotics that also combine, like I mentioned, language and vision and action together. And so here in particular, we see, I revised my stance on language models, which is a year ago, I felt that we need something that competes with language model, right? But is more grounded in vision than in language. But actually, and as any good scientist, this is actually a falsifiable hypothesis. We can try to push the limits of language in the team for more driving or robotics applications, and I've been surprised. I think that's the experience of a lot of people. I mean, a lot of people like Q here. You type a couple of things in ChatGPT, and okay, you're happy. But like actually pushing a little bit further, and especially with open source models that are happening now, you can find that there's actually more in depth. So maybe that's kind of like a message I can give to all of you is that if you're a skeptic, an LLM skeptic, you're actually the best placed person to test some hypothesis, to actually go beyond language and try to use them in your own field, because you will have a certain amount of critical thinking that maybe the hipsters don't have. And I found that I was in this position, and I've been pleasantly surprised by what you can do with them. So that's a message of encouragement to look at this. I know it's the hype, but if you're critical of it, it's not actually bad to go there.
Any other questions from here? Maybe we can see if someone remotely has questions. Is there any information that
Not yet.
Excellent talk. So you talked about listening the data for foundation models, and you also mentioned about vision, language, and action. The first two, obviously, people don't know how to do in collecting that corpus of data. Any thoughts on the action?
Yes, that's a really good question. So there's actually some work that's been done in conjunction with TRI, especially at Stanford. So I think with collaboration with Chelsea Finn's group. And so Steve Kamchity, Soargener, a bunch of people that we've been working with, especially Tom Collar in my team that leads the interaction team, has been working with them quite a bit on vision language and language action, vision language action together. In particular, these ideas of using language as some kind of semantic measure. I think that's a similarity that's important, but more recently, conditioning. So language conditioning, I think is really important. And I think more broadly, there's also like exciting works that have been going around for a while, like in DeepMind and in Google Brain, or like DeepMind. So DeepMind and DeepMind, Google DeepMind, I guess. They basically where they do like Palmy, I think is probably the more recent one, where they embed language, embed vision into the embedding space of language so that they can mix together. What this buys you is this buys you like you can extend the input from just text to text and image. And then once you have text and image together, you can close the loop and you can formulate your objectives in language. So this is where the language conditioning happens. You can do image conditioning. You can even use stable diffusion to generate goal images, which I think people have done in Sergey Levin's lab. I think Dhruv Shah has done work like that. So what does it actually mean? If it means a goal, if it means task planning or state planning, there are a lot of people that work on action being high-level tasks that can be described in language. And once you're there, you're in LLM land. For actual control, when you're talking about low-level control, there's very little work on that yet. We have some exciting internal results in the team for that currently, both from the perspective of language, but also from the perspective of actual like safety and low-end control and like these control bearer functions that I just mentioned earlier. So there's some work. It's probably where the frontier in robotics is at now in terms of the action. But I think you'll see a lot of exciting work coming real soon, including from us.
Any final questions? Else?
And, one more.
Questions from online audiences?
Hi. So, thank you for the really nice talk. So I just have a question that, seems like a lot of your work focuses on depth as well, depth estimation. But don't you think, it's been a lot of time since we as a community are stuck with the depth, and we can maybe move beyond it, like something, to something like time conclusion or something, because depth is not our ultimate goal. In fact, in autonomous driving, you have two objects, one is moving vertically, one moving in opposite direction. So other way you're like time conclusion and more important. What do you think?
Yeah, I think that's right. I think what's interesting is if you look at what happened in the history, we went from no machine learning to a lot of machine learning models in perception with like specialized machine learning modules, right? So actually, detection, tracking, but even some kind of very ad hoc small machine learning models like car detection or time to collision prediction, etc. And so what happened very quickly, and I think for a lot of the people that have been working and designing these stacks for a while, you get a proliferation of models. And you get a system that becomes very complicated to reason, huge pressures on the GPUs, on the onboard compute. And so then there was an extension of machine learning when GPUs available to a contraction, which happened in the form of multitask networks. Just merge the backbones wherever you can and add heads, and then your heads become as complicated as the backbone, and then you're like, right, and then you go back. So you have like this kind of like mitosis that regularly happens, like map reduce kind of thing that happens. I think after seeing a couple of those oscillations, you wonder, is there a better way? And especially the multitask way, you would think, well, why don't we have just one backbone, a really big backbone, and then very small heads, or very simple ways to describe the task, maybe language condition, etc. And just do all these tasks that matter, like time to collision, etc. we care about, but do them at the marginal costs on top of a better backbone. And if you want to call a foundation model a better backbone, I think it's reducing it, but I'd be okay with that. I think that's not so bad. And so really the whole point of this is amortized computation. I talked about it from the perspective of amortized computation of training time. Do one big mega training run, and then you can have many small heads that you keep the rest frozen, etc. You can even have like sub tokens. You have all kinds of things even in the inputs, like the stuff I talked about with the self-calibration. You can extend it to other ideas. But it's also at test time you amortize the computation, because if you say I want to capture my latent representation that captures all these various interests that I have, all these various tasks, TTC, like linker state, you can imagine there's a bazillion tasks you care about inside the stack. You also want to amortize the computation at inference time. And so the foundation model is to try to nail that backbone. In a way, you want to see it as like one way to say like nail that backbone, really. The question is it because of joint training around all the tasks? I don't think so. Having tried that myself for a while in the team, you always have new tasks. And so you always have these problems of competing, like in multitask learning, it's called task interference, right? And then you have the continual learning setup. So you have a lot of problems. I think the promise of foundation models is really you nail that pre-training once, and then keep it frozen, and then you can add stuff on top. And they don't need to do a tug of war on the abstract representation. All the representations be, I really want to be better at yellow lights. No, I really want to be better at child detection. Well, you want both, but you don't want them to interfere. And so that's, I think for me, it seems like the foundation model is a better architecture for that, because you keep it pre-trained, frozen, and then you can add tasks. Even different teams can add different tasks on top of it without competing with each other.
think I have time for one final quick question. Okay, yeah, you can go.
Cool, so many questions, thank you.
Yeah.
Hi, and what's your stance on synthesis data or simulated data, given that it usually is created using the same geometric filter that you use to train your models?
Great question. Travel back in time 24 hours. And I gave a talk on this yesterday at the synthetic data workshop. Joke aside, it's recorded, so you can check it out. The long story short is I'm a big fan because I said this talk, like, we're never gonna have enough data. I meant we're never gonna have enough real data. And I said we fill in the gaps with our principles, but there's actually another huge shovel that can help us fill the gaps, which is synthetic data. And so essentially there's three big things. There's the known knowns, there's the known unknowns, and there's the unknowns, right? And so I think the known knowns is what you have in the real world, what you labeled tiny fraction of your data. You have the known unknowns, which is the things you know, should be in the data, but you don't see it necessarily, or you don't have it in your data set, or mining it sufficiently, it takes forever. So you can actually, if you can program them, you can have your simulator generate those known unknowns. And then you have the unknowns, which is either you have principles that embed a fundamental common trait between all these unknowns, right? You say, I don't know how, people would react to this robot, but I know they don't want to be, hurt. And you can have like general considerations there that generalize across people. So principles, or, you can have, or you do self-supervised learning, where it says, you use all the data without curation, without etc., and you just train on all data, and nobody's going to ever look at it. The danger with that, and actually we've done a couple of papers with Stanford on learning theory, which is we know